So this is a video about the technique of integration by substitution, and a lot of the skill of integration by substitution is based on pattern spotting, and therefore one of the exercises that I have put in this list is actually not of the right pattern. So one of them you will not be able to calculate. Integration by substitution will not help you, and that I think is an important skill, realizing when the technique does not work. On top of that, another one of the exercises requires not just using integration by substitution, but doing a little bit more work afterwards. So again, you will, I hope, be able to recognize at the time which one it is. So what I suggest you do is that you write down each one of these integrals on paper, work through them, having paused the video, and then once you think you've done them, or done enough to start, you can then continue playing the video, and I will give you the answer to this one first, this second, this third, this fourth, this fifth, etc. So I hope you enjoy working through the exercises, and with this I suggest you pause the video. Okay, welcome back. Let's move on to the next slide and go through the answer to this question, which I hope you have already solved. So in this first exercise we want to integrate theta multiplied by the sine of theta squared, and we're going to use the substitution formula here. Why are we going to use it? If you look at this integrand, the thing that makes it look like it might be very difficult is the argument of the sine function, this factor of theta squared here. And if we didn't have this factor of theta outside, this would indeed be a difficult integral. So we have here a factor of theta, and we recognize that up to a multiplicative number, theta is the derivative of theta squared. And as soon as you recognize that, as soon as you spot that pattern, you can be happy, because it tells you you're going to be able to use the substitution formula and to calculate the integral. And with practice you might even just write the answer down immediately. But let's be a little bit slower and let's just recognize what we're trying to do here. So we look at the argument, and we're going to call that is our new variable. So we're going to say let u be theta squared. And that way, when we've made this replacement, we're going to have f, which is the sine of u, integrated with respect to u. That's the aim of what we're trying to do. So u is theta squared, and that means that du d theta, the derivative, which we're going to need for our substitution formula, is going to be 2 theta. Now if we look at our integrand, we don't have 2 theta here, we just have theta. But we can always write our integral I1 as a half, it's just a number so I can take it through the integral, sine times 2 theta times the sine of theta squared integrated with respect to theta. So when I look at this, I see that I can write it in this way. This is my new variable, this is the derivative of the new variable with respect to the variable that I'm integrating with respect to initially. So I can write this as a half, and then I have the sine of u. This is du d theta integrated with respect to theta, so that's equivalent to just integrating with respect to u. This is now a standard integral, so the integral of sine is minus cos, so we have minus a half cos of u plus an integration constant perhaps, and we can check the minus sign by differentiating this, and when you differentiate the cosine you get minus sign, minus times minus will become plus, so we'll get back to the initial integrand. And this tells us that I1 is minus a half times the cosine of theta squared plus an integration constant. So that's our result, and what we can do, and what we should do, is to check it. And the way we check such integrals is by differentiating the result and verifying that we obtain the original integrand. So integration by substitution is the integral equivalent of the chain rule, so it's not at all surprising that when we differentiate this we're going to need to use the chain rule. So what we find is that the derivative of I1 with respect to theta is going to be minus a half sits there. The derivative of cosine is minus sine, so I'll immediately change the sign out front. I make this plus. I have the sine of theta squared, and then I multiply this by the derivative with respect to theta of the argument of the cosine, and that was theta squared. This derivative is 2 theta. The 2 and the half here will cancel, so I will be left with sine of theta squared times theta, or written more nicely, simpler term first, theta times the sine of theta squared. And that we recognize as the initial integrand, and that tells us that we have correctly calculated the integral. So with that, we can move on to the next integral, having realized that the key steps in this were to recognize, first of all, that this is the factor that makes the integral difficult, but that out here, up to a multiplicative number, we had the derivative of this argument, and that allowed us to perform it using the substitution formula. So in this exercise, this integral here, which I'm going to call I2, in this integral what we have is phi multiplied by the square root of 1 plus phi squared, and this factor here is the term that looks difficult. However, again we recognize that what we have here is the derivative of the argument of the square root up to an overall number. So what I'm going to do is I'm going to be using the following version of the substitution formula. So we're going to use that the integral of some function of a variable, let's call it phi, to the power n, multiplied by the derivative of this function with respect to phi, then integrated with respect to phi, is the integral of the function to the power of n plus 1 over n plus 1, or it is the logarithm of the modulus of the function if n is equal to minus 1, and here we have assumed that n is not minus 1, because in this formula here, if n is minus 1, we're dividing by 0. So this is the key formula that we are using, and again, it is straightforward to verify this formula. If you differentiate this, you will regain this using the chain rule, and if n is minus 1 and you differentiate this, you will regain 1 over f times df d phi. So that's a good thing to check, that differentiating this for n is not minus 1 and differentiating this with n is minus 1 regains the integrand here. So that's what we're going to use. Now let's look back at here. Our integral I2 is going to be 1/2 times the integral of 1 plus phi squared, all to the half, that's what the square root means, multiplied by 2 phi integrated with respect to phi. So again, just as in the last example, what I've done is I put a factor of a half here and I put a 2 here. So all I've done is I've multiplied by 1 in a way that makes the integral easier. And now we look at this and we see that this integral is of exactly this form. This is 1 plus phi squared, that's f, all to the power of a half, multiplied by the derivative of f. The derivative of 1 plus phi squared is 2 phi, and so this is of this form with n being equal to a half, and a half is not minus 1. So what we have is that this integral is a half. We have to, from this formula here, take the power and add 1 to it. So we have 1 plus phi squared to the a half plus 1 is 3 halves. Then we have to divide by this new power, and dividing by 3 halves is the same as multiplying by 2/3. And that's our result up to a possible integration constant. So we can simplify here, because we see that we have a half and a 2 that will cancel. So we realize that overall I2 is 1/3 1 plus phi squared to the power of 3 halves plus an integration constant. And that is our result. Again, what we can do and what we should do is to check it. So to check, again, we differentiate our result with respect to our variable phi. We have 1/3 that's just sitting there. Now we differentiate something to the power of 3 halves, so we pull the power down. So we pull down a 3 halves. We reduce the power by 1, so that's going to reduce it to a half. And then we multiply by the derivative of the argument, the derivative of 1 plus phi squared with respect to phi, and that's going to give us 2 phi, again just using the chain rule. So we look at this and we see that the 3 and the 3 cancel. We also see that the half here and the 2 cancel, and we are left overall with phi that I'll just put in front, that's just this factor, times 1 plus phi squared to the half, or if you wish, the square root of 1 plus phi squared, and that is our initial integrand. So we realize that yes, we have correctly calculated this integral. So again, I recommend very much that you verify that this is true by differentiating these formulae here. And let's move on now to the next example. So this exercise is essentially identical to the previous exercise, the only difference being there's a minus sign here that we have to be careful with. And we could do it in the way that we did the second exercise, the integral I2 with, but I'm actually going to do it just for fun in a way similar to how we approached the first integral. The different methods are completely equivalent. So let's just say that we're going to look at this, and we're going to say that the argument of the square root is the thing that's difficult. So we're going to let u be equal to 1 minus phi squared, and that means that du d phi is minus 2 phi. So this tells us that we want to write our integral I3 as the integral of the square root of u, that's this factor here, and I'm going to put the phi at the end, and I want to write not phi but minus 2 phi, which is du d phi, so that's du d phi, but that means that I've put in a factor of minus 2, so I better put in the number here multiplying it as well, so I put in a factor of minus a half, so that the minus a half and the minus 2 overall just correspond to having inserted a factor of 1. And then of course we have to integrate with respect to phi. So therefore from the substitution formula that we wrote down in exercise 1, so I'll just write it out again, the integral, some function, and its variable now f of u of phi multiplied by du d phi integrated with respect to phi is equal to the integral f of u integrated with respect to u, and at the end we replace u by u of phi. So this therefore tells us that our integral I3 is minus a half, and it's the integral of u to the half with respect to u. So what I've done is I've recognised that the square root of u is u to the half. So this is going to be, I add 1 to this power, so that becomes 3 halves. So I have minus a half. I'll leave a bit of a gap here. I'll write u to the 3 halves, that's my new power, and then I divide by the new power, so that means I put in a factor of 2/3. And then I add an integration constant. So tidying this up, we'll cancel the half and the 2, and we're going to obtain that therefore I3 is minus 1/3, and what was u? U was 1 minus phi squared, so we have 1 minus phi squared all to the power of 3 halves plus an integration constant. And that's our result, and I will leave that for you as an exercise to check. It's identical to the previous example except for another sign, so check by differentiation. And as I say, that is just the previous case but with an extra minus sign in the argument of the square root. So with that we can move on to the next example. So the fourth integral, the integral of 3t divided by t squared plus 1 cubed, can be calculated either by saying that u is t squared plus 1, or what we can equivalently do is we can recognise that this has a particular pattern, and it has the pattern some function of t to the n multiplied by up to a multiplicative constant df dt integrated with respect to t, and this is going to be f of t to the n plus 1 over n plus 1 for n does not equal minus 1. Otherwise it would be a logarithm. But in this particular case we don't have n is minus 1. So let's just see why this is the case. Well, what we have is that I4 is equal to the integral. Now I'm going to pull the factor of 3 that's here outside because it's actually a distracting factor. It's not a helpful one. So let me just pull it out. And then we have the t squared plus 1 all to the power of minus 3. So we have t squared plus 1 to the minus 3, and minus 3 is of course not minus 1. And then we are left here with a factor of t, and what I can do is I can recognise that t is a half times 2t integrated with respect to t. So again, all I've done here is I've put in a factor of 1, and the factor of 2 here is because 2t is the derivative of t squared plus 1. So therefore what we have is that I4 is, now we have a factor of 3 there initially, and here we have a factor of a half, so I'm going to take the half out. So we have 3 over 2. We have the integral t squared plus 1 to the minus 3, and then we have d by dt of t squared plus 1 integrated with respect to t. So I've just done this rearrangement to make it absolutely clear that this is of this form with f of t being t squared plus 1. So from our result for this integral, which again you can easily check by differentiating this side, that it gives you this integrand, what we have is 3 halves that was there initially. Now here is our function to the power of minus 3. We add 1 to it. Minus 3 plus 1 is minus 2. So we have t squared plus 1 all to the minus 2, and then we want to divide by this new power, and dividing by minus 2 is equivalent to, we put a minus sign in the front and we put a factor of a half there, plus an integration constant. So we can tidy this up and we see that I4 is minus 3/4 1 over t squared plus 1 all squared plus an integration constant, and that is our result for this integral. So again, of course, what we can do and what we should do is to check it. So we want to differentiate our result with respect to our variable t. We have minus 3/4 at front. Here we have t squared plus 1 all to the power of minus 2, so we're going to pull down a factor of minus 2. I'll put that in brackets to make it clear that this is multiplying this and not subtracting from it. So we have minus 2. We have then 1 over t squared plus 1, and we've got to lower this power. It's on the bottom, so that means we have to the minus 3 overall. And then we multiply by the derivative with respect to t of t squared plus 1, which is going to be, of course, 2t. So tidying all of this up, what we're going to have is, well, first of all, we notice that the minus signs will cancel. We're going to have a factor of 2t from here. 2 times 2 is 4, so the 2's and the 4 will cancel. We're going to have a t left and a 3, so that's 3t. So we have 3t left on top, and on the bottom we have t squared plus 1 all cubed. So that again tells us that we have correctly calculated the integral because this is our original integrand. With that, we can move on to the next exercise. So in this integral, we want to integrate 1 over w multiplied by the logarithm of the modulus of 7w. And it's helpful if we recognize that the derivative with respect to w of the log of the mod of 7w is just 1 over w. Now, if you're not completely confident with this, there are two different ways of seeing it. One way is the following. You say that this is d by dw of the logarithm, and now it's 7w, so it's the logarithm of 7 plus the logarithm of the modulus of w. The logarithm of 7, its derivative is 0 because it's a constant, and the derivative with respect to w, the log of mod w, is just 1 over w. An alternative way of tackling this is to use the chain rule, perhaps slightly more tedious. The logarithm of the modulus of 7w is then going to be, by the chain rule, 1 over this argument, so it's 1 over 7w multiplied by the derivative of the argument of the modulus, and that is 7w. This derivative is a 7. The 7 and the 7 here cancel, so we are left overall with 1 over w. Both roads lead to Rome, as they say. Both techniques are equivalent and give this same result. So what we recognize is here we have the derivative of this logarithm, multiplying it, and we can use one of our standard substitution formulae. So let's say that u is the logarithm of the modulus of 7w, du dw is 1 over w. So this tells us that our integral, I5, is the integral of, now I'm going to write the logarithm part first, but that is just u, multiplied by du dw integrated with respect to w, and from the substitution formula that's just the integral of u with respect to u, and that is 1/2 u squared. We add 1 to the power and divide by the new power plus some integration constant. So therefore I5 is 1/2, and u was the logarithm of 7w, so this is the logarithm squared of the modulus of 7w. And I emphasize that what I mean by this is the logarithm of 7w all multiplied by the logarithm of 7w. It is the logarithm squared, not the logarithm of the square. Completely different thing. So this is our result. Let me add an integration constant, and what again we can and should do is to check by differentiation. So to do that I'll just make a little bit of room. So we want to differentiate I5 with respect to w. We have a factor of 1/2. We then have the logarithm squared, so we bring the 2 down. We have the logarithm then to the power 2 minus 1, that's just the logarithm of 7w. And then we multiply this from the chain rule by the derivative of the logarithm of 7w. And as we explained here in detail, the derivative of the logarithm of 7w is just 1/w. So we see here that the 2 and the 1/2 cancel, and we are left with, as we hoped, 1/w times the logarithm of the modulus of 7w, and that shows, because it is the initial integrand, that we have correctly calculated our integral. So now we can move on to the next exercise. So when we look at this integral here, we see that we have the logarithm of the modulus of w plus 7, and out here we have a 1/w factor. So one might for a split second think that one can use integration by substitution, but if one thinks about it, this is not going to be the case. d by dw of the logarithm of the modulus of w plus 7 is going to be 1/w plus 7. And bear in mind that this logarithm, the logarithm of w plus 7, cannot be simplified. The rules for logarithms do not allow that. And 1/w plus 7 is not the same, obviously, as 1/w, which is what we have here. So therefore, this integrand does not fit into the scheme of integration by substitution. So this integral cannot be integrated using integration by substitution. And it's actually a very complicated integral, and the answer involves functions called dilogarithms, so if you don't know anything about dilogarithms, you are not going to be able to calculate this integral. So with that, I'm going to stop. Having first perhaps though encouraged you to actually just try it, play with it a little bit, and realise that you find it very hard indeed. So the seventh exercise is to integrate 1/w plus 7 multiplied by the logarithm of the modulus of w plus 7. So what we think about, after we look at this for a moment, is that 1/w plus 7 is the derivative of the logarithm of w plus 7. So we note that d by dw of the logarithm of the modulus of w plus 7 is 1/w plus 7. So this tells us that if we say u is the logarithm of w plus 7, that's going to be our new variable, then this factor of 1 over w plus 7 is du dw. So therefore we can use this substitution and we get that I7 is going to be the integral of u, that's the logarithm of w plus 7, multiplied by du dw, integrated with respect to w, and from the substitution formula that's just going to be the integral of u with respect to u. So this is going to be 1/2 u squared plus an integration constant, so therefore our integral I7 is 1/2, and u, we remember, was the logarithm of the modulus of w plus 7, so we get 1/2 the logarithm squared of the modulus of w plus 7 plus an integration constant, and that is our result. And checking this is very much like exercise I5, so I will leave that for you as an exercise. So exercise, check this by differentiation. And with that we'll move on to the next exercise. So the next exercise is to calculate the integral of the cotangent of theta with respect to theta. And unless you know off by heart what the result is, you have to think about what cotangent means. So what it means is it's the integral here of the cosine of theta divided by the sine of theta. And the cosine of theta we recognize as being the derivative of the sine of theta. So this entire integral has the form of the sine of theta all to the power of -1, and this does not mean the inverse function, it means the reciprocal function 1 over sine theta, multiplied by the derivative with respect to theta of the sine of theta, which is of course the cosine, integrated with respect to theta. So this integral has the form of the formula that we have seen before. So we recall that the integral of 1 over some function of theta multiplied by df d theta integrated with respect to theta is the logarithm of the modulus of the function of theta plus an integration constant. So therefore our integral I8 is equal to, our function f is the sine function, so we have the logarithm of the modulus of the sine function. Logarithm the modulus of the sine function plus an integration constant. And again, this is a result that we can and should check by differentiation. So let's check the derivative with respect to theta of our integral I8. Well, the derivative of the logarithm of the modulus of something is 1 over the something, so this is 1 over sine of theta multiplied by the derivative with respect to theta of the argument of the modulus of the logarithm. So here we have sine of theta. This is the cosine of theta, so we have the cosine of theta divided by the sine of theta, so this is indeed the cotangent of theta and we realise that we have correctly calculated the integral. So with that we can move on to the next exercise. So the ninth exercise is to integrate the tangent of theta multiplied by sec squared of theta. And for a split second this may look fairly horrible, but then I hope you recognise that sec squared of theta is the derivative of the tangent of theta. So therefore, once we recognise that the derivative with respect to theta of the tangent of theta is sec squared theta, then this tells us that I9 is the integral of the tangent of theta multiplied by the derivative of theta with respect to theta of the tangent of theta integrated with respect to theta. So if we call this factor here u, then this factor here is du d theta. We're now going to integrate this product with respect to theta, so by the substitution formula, this tells us that I9 is equal to the integral of u with respect to u, which is once again just a half u squared plus an integration constant. So therefore I9 is 1/2 the tangent squared of theta plus an integration constant. And that again is something that we can check and should check. So what we want to do is we want to differentiate with respect to theta our result and see that we indeed obtain the original integrand. So we have here a factor of 1/2. When we differentiate something squared, we're going to pull the 2 down. We are going to reduce the power by 1, so we're just going to write the tangent of theta. And then we multiply this from the chain rule by the derivative of the tangent of theta with respect to theta, and that is sec squared theta. And we see immediately that the 1/2 and the 2 cancel, and what we are left with is our original integrand, so therefore we have indeed correctly calculated the integral. With that we can move on to the next exercise. So the final exercise in this video is the integral of rho cubed times the sine of rho squared. So when we first look at this, we realise that the argument of the sine function rho squared is going to make this a difficult integral. So it's very natural for us to say let u equal rho squared, and that means that du d rho is going to be 2 rho. This, we hope, will make the integral possible for us. But now we look at our original integrand and we realise that we have not 2 rho or 3 rho or 7 rho, but rho cubed. So for a moment we might think this is impossible, but actually it is possible, but it's going to require a bit more work. So let's see why. What we have in our integral I10 is we have the integral of, and now I'm going to split this rho cubed up into rho squared times 2 rho, and if I'm going to put this factor of 2 here, I must put a 1/2 outside. And then this is multiplied by the sine of rho squared with respect to rho. So all I've done here is I put in a 1/2 and a 2, so this is just a factor of 1 overall, and I've broken up rho cubed into rho squared multiplied by rho. Now, the reason why this is going to work is what I have here, rho squared, is u. So I'm going to have u times the sine of u, and the 2 rho factor I can put at the end as du d rho integrated with respect to rho. So what I have is 1/2 the integral of u sine of u, and then we have du d rho integrated with respect to rho. So from the substitution formula, this is 1/2 the integral of u sine u integrated with respect to u, having used substitution. Now, when we look at this result here, this is an integral which we are going to be able to calculate using integration by parts. I'd like to emphasize that if we'd had, say here originally, rho squared, then this integral would be extremely hard. Supposing we had rho squared here, when we did the equivalent of this breakup here, we would have a rho times a rho, so this would not be rho squared, we just have one factor of rho left, and a factor of rho would be the square root of u. So we'd end up with the square root of u times the sine of u, and that again is a very difficult integral. So this is really possible because of the rho cubed. And generally speaking, if we had rho to the 1, this would be a straightforward integral. It's actually exercise 1, the first of these exercises, with theta replaced by rho. Rho cubed is doable, but it requires a bit more work. We're going to have to use integration by parts. Rho to the 4th would be extremely hard. Rho to the 5th would be doable. It's just going to require repeated use of integration by parts. So I encourage you to play with different powers and explore which powers are possible and which powers are extremely difficult. So now, having said all of that, this is an integral which we can calculate using integration by parts, so let's do that. So this is our result for I-10, and what we're going to be using now is the integration by parts formula. So integration by parts, and I don't want to use u and v because I'm likely to get confused, so instead I'm going to say that we have the integral of f times the derivative of g with respect to u is equal to f times g minus the integral of the derivative of f times g integrated with respect to u. And what we have to do now is to choose in this integrand which of our 2 factors we're going to call f and which of our 2 factors we're going to call the derivative of g. And to do that, we're going to use our mnemonic late. So late tells us that we should choose the factor that we're going to differentiate according to the, if there is a logarithm, we should choose that first. If there is an algebraic factor, we should choose that second, trigonometric factor third, and an exponential factor fourth. We look at this integrand, we have an algebraic factor and a trigonometric factor. So from late, we're going to choose the algebraic factor to differentiate. So therefore, what we're going to do is we're going to say that f of u is u, and the derivative of that is very easy, it's just 1. And we're also going to say that the derivative of g of u is the sine of u, and that means that g is going to be the integral of that, and that is minus cos of u. So that when we differentiate that, we get the sine of u. So now we've prepared all the ingredients for integration by parts. We have the formula explicitly here, so this tells us what I10 is. I10 is, there's a factor of a half multiplying everything, so I'll open brackets, and then we're going to have f times g. F is u, g is minus cos u, so u times minus cos u is minus u cos u. We then subtract the integral of the derivative of f, which is just 1, times g, which is minus cos u, so there's a minus sign there that we have to be careful about. That's going to make this positive, and then it's the integral of the cosine of u with respect to u, close brackets. And this integral is a straightforward integral, it's just the sine of u, so therefore we conclude that I10 is 1/2, and as I've said, this factor is just the sine of u. Because that has a minus sign and the sine of u is simpler than this, I'll write the sine of u first. So I'm going to say it's half the sine of u minus u cos u, close brackets, and that is our result for this integral. Having said that, u is not our original variable, which was rho. U is rho squared. So we have to rewrite this in terms of our original variable, rho squared. And to do that, I'm going to have to make some room. So what we see is that I10 is 1/2, open brackets, and it is the sine of rho squared minus rho squared times the cosine of rho squared. So that's our final result for the integral, plus perhaps an integration constant. And what we should do now is to check that we've got it right using differentiation. In other words, if we differentiate this, do we regain our initial integrand? So to do that, let's differentiate I10 with respect to rho, our variable, and we have a factor of 1/2 that multiplies everything. In the first term we have the sine of rho squared. We differentiate this using the chain rule, so we're going to get the cosine of rho squared multiplied by 2 rho. That's just the derivative of the argument here. For the next term we're going to need to use the product rule and the chain rule for differentiating this factor. So when we hit this with the derivative operator, we're going to get minus 2 rho times the cosine. So we have minus 2 rho times the cosine of rho squared. And then when we hit the second factor here, we have minus rho squared. The derivative of cosine is minus sine, so I'll put sine of rho squared and correct the sign here to make it positive, because minus times minus is plus. And then in this factor I still have to multiply by the argument, the derivative of the argument, the derivative of rho squared with respect to rho, and that's going to give me a 2 rho. All I'm doing here is using the chain rule, close brackets. We look at all of this and we realize that this factor, or this term, and this term are exactly the same. Here we have the 2 rho at the end, here we have the 2 rho at the beginning, but they're the same. So therefore these factors are going to cancel. I'm left with what's left with here, and I notice that I have 2 here and a half here, so they will cancel. I have here a rho and a rho squared, so they're going to combine to give me rho cubed, which is what I want, and a sine of rho squared is also here, which is what I also want, so I realize that we have correctly calculated the integral. So in this final example it was a little bit more difficult because we couldn't just immediately almost guess the answer. We looked at it, we could see that there was a possible substitution to make this a doable integral, and then when we did that we were able to do it, but only once we used another integration technique, integration by parts. And with that I'm going to stop this video.